say given dB, in the next let us consider compute the corresponding dA first, which is followed by computing dk. We now have the value in A and K and dB, and this is our target. The technique is try to understand how the change in one element, for example I and j. Let me take a better view of that. See, it's here. If I change this element by a small amount, how that would affect L. To understand this, let us consider how this element contribute to the corresponding elements in dB. So if this is the ith row and the jth column, of course, this will affect the corresponding ith row and jth column in dB. And how? Recall that we would apply the kernel. See, I will use this as my kernel. I call that K, of course. Let me select this and move here. So the kernel will be applied here. By applying, we will multiply the corresponding elements in the kernel and the elements in the input array, and let that to be added to the corresponding element in the output array. So without too much difficulty, but we just need to some careful care, we can calculate that this element A, I, and J will contribute to the corresponding B, I, and J by a factor of K, 0, and 0. Okay, so it will affect the corresponding element in the output array by a factor of the up left corner of the kernel. Okay, so, and we know, we have already known that this element will affect the final object function by a factor of dBij here. Okay, okay, sorry, I think the arrow is not accurate. The arrow is actually, it will affect this, and we have known that this effect of the final function L is by a factor of dB I and j. Okay, I remove some clutter here. Okay, and maybe I just put it here. Now we have found one part of this element in the input array to the output to the final object function, that is K 0 and 0 times dB I and j. Okay. We will multiply the dBij with the factor by which aij contributes to net. However, this is not the only part in the array B that receives the contribution from the corresponding element from A. Look at the actually, if we consider the movement of the kernel, I accidentally changed the color of my kernel here. If we consider the movement of the kernel, we will find that. Let's do that. This the contribution to the corresponding Bij is actually the last step at which this element in the input affect any output elements in B. In one step before the kernel have moved to here, for example, the up left corner of the kernel is aligned with one element before the element of interest. Now the element of interest also contribute to another element in B. It's about here, which is of the same line, same row I, but to the element of G minus 1. And now, sorry, it is by the factor of K 0, 1. So correspondingly, we can, using the same kind of analysis, we now add another contribute to the final object function by the element ij element in the input to the object function by k 0, 1 times db I g minus 1. And db, db, recall that, refers to how each element in B will affect the objective function in the end. So we can use this kind of argument over time again. We will find that in terms of the horizontal direction, this element first start to affect any element in B when the kernel is at the location about here. So when the width of the kernel barely touches, just reach this location, it starts to affect any element in B. If we compute that carefully, that would corresponding to the element in B of D, B, I, and G minus K plus 1, that is K elements to the left. Of course, assumingly, this is not over the boundary of B, which is 0, okay? So that is K, 0, K. We can apply the same kind of argument in the vertical direction. So I accidentally changed the color again. Okay. So when the kernel up left kernel is aligned with one element above the ith row, it will affect the corresponding output element. Okay. Now we will consider its effect on on B element I minus 1 and J, and that will be the contribution factor will be the second row of K here. Okay, so it will be K 1, 0 times this. So you start to get the pattern. Actually, the contribution of this element in A to the final output will be collected using the same kind of using the kernel to cover an area of an array and collect the, by collect I mean take the sum of the element-wise product between the element of dB and K, which itself is also a convolution operation. Just in this time, because we have considered the the pattern that this element contributes to which elements in the output array are associated to which location of the kernel. We need to flip the kernel horizontally and vertically, and using the flipped kernel to convolute with the gradient of the object function of the output, we can compute the gradient of the objective with respect to the input. Okay, I know this argument feels a little bit convoluted, you need to maybe watch it over again, let the information sink in your mind. But later we will show a tutorial on how to implement this and how to verify this kind of computation.